Can you all hear me?
Yes, sir.
Okay, good. And is the screen properly visible to everyone?
Yes, sir.
Okay, thank you. Yeah. Okay, so then let's start. So basically, the topics we'll be covering, we'll be actually going through the topic of DC circuits, where some of the questions would be directly related to Kirchhoff's law. So that's why I guess some of the message that's what the topic I wrote. So Kirchhoff's law and moreover DC circuits. So to just to like recall this to everyone. So there Kirchhoff's law. There are two laws of Kirchhoff, and these laws, to like understand them in their context, uh, this person Kirchhoff realized that this is how. Okay, so this phenomena of electricity was a bit new to people. Like all of a sudden, if we apply had this stuff how they were inducing electricity by chemical reactions or either by electromagnetically inducing them and stuff. So this phenomena or this flow of current was something new to them. So back then they were just realizing how this thing works. So this person Kirchhoff came and he realized and he made some laws that basically define how current or this electricity thing interacts with each other. So the first law of Kirchhoff was that the uh, sum of currents, sum of I entering a node, entering a node equal to the sum of currents, the sum of I leaving the node. So this was this person's first law that if I have, let's say, a node is a point where there are multiple wires which are connected. So this point where they are connected is known as a node. So that's what a node is. So if for example if this is a node and then there's this wire bringing in a current I1 I, and then there's another wire bringing in another current I, and then there's another wire bringing in another current I, and I'll give these values later on. So and then there are two wires giving out with a current, and if I now were to just give them some values, so what he said is that the total current entering, for example if this was 2 ampere, this was 3 ampere, and this was 5 ampere. So the current that was leaving was also 3 amperes and 7 amperes. So the sum of the currents that was leaving the node was equal to 10, which was also equal to the sum of current which was entering the node. So that's what the law stated, that all these currents are supposed to be equal. And obviously, we know what current is. We know that current is equal to charge over time. The charge that passes, the charge that passes through a point per unit time. So obviously, if the time we remove the time part for a moment, so what we realize is that the charge entering a node equals to the charge leaving a node. So now today, when we know that the movement of charge or this flow of charge is due to electrons, which are particles, and obviously they have a finite quantity and they can't be uh, reduced by a person, or we can't generate or create electrons. So we know this. So obviously the number of electrons that would be entering the node would be equal to the number of electrons that would be leaving the node. But back then they didn't know this stuff. So this charge and this whole thing, this current was something new to them. So this conservation of charge or this idea comes from this Kirchhoff's law, that charge is always conserved. So the charge that entered the node was equal to the charge that would leave the node. So that's what the law is. And then the second law was that the sum of EMF in a loop equals sum of potential difference in the loop. So one thing for this is that the loops must be same. So if my loops are same, that I'll come to what loops are. But the idea is that in the same loop, the sum of EMFs equals the sum of potential difference. And now if I have a circuit, which I just draw myself like this, this is, I'm just drawing things to make sense what a loop is. So if I want to talk about what a loop might be here, so I could say that this thing is a loop, and I could say that this thing is also a loop. So these things, they all are loops. This is a loop of current, and that's another loop of current. And similarly, I could say that this whole thing and inside it is also a loop. So loop is basically a whole region of wire, a whole region where the wire extends. So that's what a loop is. So this idea was that the sum of EMFs in a loop equals sum of potential differences in a loop. So another way to phrase this could be that if I just draw a loop in front of me and just assume that this is a loop. So the sum of EMFs, the EMFs that would be adding, and what's an EMF and or what's potential difference? Okay, so if this is a loop and there are EMFs involved, what EMF is or what's voltage? Can anyone tell me what voltage is? What's the formula for voltage?
Work done over charge.
Work done over charge. So work done over charge. So obviously work done over charge, and inside in a loop the current is the same. So the flow of charge is the same. So in other words, what this law tells us is EMF is energy supplied into the circuit, and a potential difference is energy extracted from the circuit. So energy supplied into the circuit should be equal to the energy that is extracted from the circuit. So that what this law basically is, and it's another way to sum the law of conservation of energy. Okay, so this was a brief summary of what Kirchhoff's law were. And then there's another thing. There's this formula for current, which we know. So the previous formula back in O levels was simply I equals Q over T, which is very valid and which is essentially the actual formula for current, Q over T. But there's also another formula which is a result of this formula, and in that formula we kind of utilize the properties of the wire, the drift velocity and stuff like that. The formula of that formula is equal to N Q A T, or yeah. So N would be the number of electrons per meter cube. So number of electrons per meter cube. So that could be that is N, which is also known as the number density. Q is the charge of carrier. If it's an electron, a single electron, then the charge is plus a negative one, or if we're talking about positive charges, that would be plus one charge of carrier. Then there's A. A is the area of cross section. So that's what area is. And then I have V, which is the drift mean velocity. So A was the area of the conductor, which is the conductor that's conducting this electricity. And drift mean velocity is the mean velocity by which electrons drift through that conductor. So that's what this formula is. So this formula is also important. And then there's this whole derivation of this formula, which you all need to know, which you can like refer to however you studied in your notes or whatever. Then the last thing which I would like to recall is the formula for resistance. There's this formula for resistance where resistance equals the resistivity times length divided by area. So there's this formula, and this is the resistivity, and this resistivity is specific to a material at a given temperature. So for example, if there's copper wire at 50 Celsius, the value of resistivity, this P or rho, whatever you call it, the value of rho would be same for different samples of copper wire at 50 Celsius. But if I change the temperature or if I change the material, so for example, if from copper I make them into aluminum, so then the resistivity, the value of resistivity would change. So there's this formula that's also important. Okay, and someone, by the way, Musa bin Shahzad said, as far as physics is concerned, doing electricity waves and nuclear along with dynamics or dynamics, AKB achieve at this time is depth and talking of particles. So I don't know what like you meant, but yes, we are doing the chapter of electricity. The electricity part mainly has two components: DC circuits, and then the part where internal resistance or practical circuits resistance is involved. But that's what we'll be doing tomorrow, and today we'll be doing electricity. So that's what we are doing. So okay, so to start off with the questions. So a network of resistors, each of resistance R is shown in figure 7.1. Calculate the total resistance in terms of R between points A and C, point B and X. So point A and point C, we need to find the resistance in terms of R between these 2 points, points A and C. So one thing to realize is this point C is basically this whole region. This whole region. I can connect the resistor which is above at any point here. It is obviously connected at point B, but I could instead connect it at any point which I have like uh, marked or outlined with pink. I will connect this resistance resistor R with anything there, with any part here, any point here. I could connect it here, I could connect it here, I could connect it here, or anywhere I like. It would give me the same results. It would mean the same thing. So when they're asking me about the total resistance in terms of R between point A and C, so that resistance would be the same as the resistance between point A point A and point B. The resistance between point A and point B would be the same as the resistance between point A and point C, because point B and point C are not any different. There is no resistance between these 2 points, and they're like essentially the same point, but just apart from each other, like a distance apart. So to find the resistance between A and C, that is simply R. So R is my resistance between point A and point C. And similarly, if I ask what's the distance between point Y and point Z, so that would again be equal to R. Or if I ask what's the distance between point Z and point X, that would again still be R, because point Y and X are not different points on the circuit. They're just distances apart, but they're essentially the same point. I could have attached my resistor to point X, point Y, or point X. It would have given me the same results. In fact, I could have attached it to any point, any point on this pink region, pink line. It would have still give me the same results. So that's what this actually is. So I have this part to say to you. If anyone has any questions about this, do ask them. Okay, so the next part would be the resistance between point B and point X. So point B and point X, and see how they're like sort of confusing us or asking us different stuff. So they could have asked me the resistance between point B and Y. Instead, they're asking me the resistance between point B and point X. And as I just told you, point X and Y are the same, and point C and point X are the same. So if I were to like simplify what the circuit actually means is that I would have a resistor R. These lines, consider them to be drawn only for our convenience. They don't have any significance, any special significance. This is R and this is R. So this would be my point B and point C simplified, and this would be my point Y and point X, because Y and X are essentially the same points. So I could say that these are my points B and point X. I don't know if it's making sense, but the idea is that B and C are the same points and X and Y are the same points. We just drawn them or shown them to be a different apart, but when it comes to the circuit does not differentiate between point B and point C. So to find the resistance between these 2 points, here obviously it's a parallel combination. There are two circuits involved. So what I do is I say R total equals 1 over R plus 1 over R, and this whole thing to the power -1. So this would give me, I think, something around R over 2. Yes. So my resistance between point B and X becomes R over 2. So this is how I found my resistance. And then they're asking me the resistance between point A and point Z. So point A is this point, and then point Z, which is the point on the right. So now the whole circuit is involved. And if I like simplify the circuit, uh, from A to B, there is this resistor R which is connected in series. Then there is a combination of BC, or the combination which I've circled, which has a resistance of R over 2. So that's uh, combined with them. And then there's another resistance R. So I could simplify this whole circuit as being A, point A, and then I go forward. I have my resistor attached, resistor R, and then I have this point B and C, and I just simplified this whole thing, and this became, or I could either write it as this whole thing, and I could write the resultant resistance, and I'll come back to this part as well again, in case someone did not understand this. This is point B and C. This would be point X and Y, and then there would be point Z, and this resistance would be R. So either I could draw this resultant circuit like this, or I could say, no, I draw it properly, which could be like this. It depends on how I need to do it. I could either write the resultant resistance and make it a single resistor, or I could draw the whole circuit combination, which is circled in red. And then this goes as Z. So R, 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 R. So if I sum all these up, and so I'll simply get R plus R over 2 plus R. So my answer comes out to be 2.5 R. So obviously I know this, the resistance of this whole region is 2.5, 0.5 hours, 0.5 R. So what I previously did was I just substituted this into a single combination, which is R. So that's how you do this, because this is a 1 mark question. They don't expect you to like apply or to solve it in the whole thing. Like you're not supposed to do something like this, that 1 over R plus 1 over R minus 1. You're not supposed to find the resistance by applying this whole formula. It's just a 1 mark question, so a quick answer would be enough. So is this part clear to everyone? Or if anyone has any questions regarding this, regarding how I made these circuits, feel free to ask. Okay, so coming to the actual questions for today, or the actual part, uh, Kirchhoff's law, and this is like one of the important parts. So two cells of EMF E1 and E2 are negligible internal resistance are connected into the network in A, as shown in figure 7.2. The current in the network are as indicated in figure 7.2. So these directions of current and these values I1, I2, I3. Use Kirchhoff's law to state the relation between currents I1, I2, and I3. Okay, so if I first, like before I get into the Kirchhoff's law part, if I just go a bit conceptual, just to improve my understanding, how many loops can I draw in this whole thing? So if I talk about this, I get 3 loops. There are 3 loops involved. One is this small loop, and this is also again a small loop, and then there would be the outer loop. So this would also be a loop, this whole region. So this would be one loop, The loop in blue would be one loop, and then there would be another loop which would be the one in pink, and then there would be another loop which would be another loop in pink. So these are the three loops which I can get from this. Okay, so use Kirchhoff's law to state the relationship between currents I1, I2, I3. So as far as currents are related, for currents we don't need to use this concept of loops. We just need to use the concept of nodes. So that's what we do. If I look closely, F and I start observing loop node B. So at node B, sum of current entering node B should equal to the sum of currents that would be leaving node B. So the sum of currents entering node B is equal to I1, sorry, equals I1. And so the sum of current, equals I1. And then there's this current entering from I1, just this, and then there's another current entering I2. So that's what I write again, I1 plus I2 equals sum of current leaving the circuit, which is what I see here, which is equal to I3. So that's how I do this, and that's my relationship between the currents. The next part, between E2 R, I2 and I3 in loop BCXYB. BCXYB, meaning they're asking me to observe this loop and tell them about these relationships and how these relationships would vary. Okay, so my loop is identified. The next thing I need to do is identify a sign for the loop. Identifying a sign for the loop, mostly we just do a counterclockwise sign. This is my sign. Now what this sign would mean is that currents that are flowing according to this direction would give me positive values, and currents which are flowing opposite to this would give me positive values, would give me which the currents which are flowing opposite to this would give me negative values, and which are flowing according to this would give me positive values. Okay, so now if I analyze this, I realize that I first talk about this region from B to X, this whole thing. So there's a current which is moving and which has R. So I need to find the potential difference across resistor R. So the potential difference would simply be equal to I3R. So by the way, the Kirchhoff's second law was sum of EMFs equals sum of potential differences. So I'll get to the EMFs later on, but right now I'm doing potential differences. I3R. And since this direction of I3 is opposite to my convention, I've taken counterclockwise currents as positive, and this is clockwise. So I write a minus sign to this. So minus I3R. That's what I get. And then I come to the next part, which is the current which is beneath this. And again, the current is opposite to my convention. So I write I2R. So that's what I do. And then I need to talk about the EMFs. And the thing about EMF is obviously the EMF is E2. But what do I do with the sign of EMF? That's something very important. Like, how do I identify what would be the sign of this EMF? So for this sign, uh, consider it in such a way that a battery, a battery which is like this, a battery which is like this would tend to move current in this direction from, sorry, just a second, something happened to the screen. Okay, so a battery which is like this would tend to move current in this direction. The current in this battery would move like this. And if the current that the battery tends to move is according to my sign convention, then that's a positive EMF. But if it's opposite to my convention, I've taken counterclockwise currents as positive. Is this EMF E2, the current that it tends to flow in the circuit, is it according to my convention or is it not according to my convention? Can anyone tell me? Anyone? Are you guys following this? What I just told? Are you getting this? How do we determine the signs? Okay, so can anyone tell me the EMFs? Can you explain part two again? Yeah, that's what I'm doing. Okay, so I'll explain it once again. So this is my loop. I what I need to do is I need to equate my EMFs to the potential difference. The second law of Kirchhoff is that the sum of EMFs in the loop equals the sum of potential difference in the same loop. So for that, I just simply write sum of EMFs, which is E2, equals the potential difference would be I3R, and then another potential difference would be I2R. So that's what my potential differences are. Now there's one thing where I need to determine the signs of these potential differences. Like I just add them, but some potential differences are negative and some potential differences are positive. So all this thing that I was just explaining was regarding how would I determine the signs of my EMFs. So for that, we take a convention. And I took a convention which was that I would take all currents in the counterclockwise direction to be positive. This means that any potential difference which any resistor which has a current that flows opposite to this convention, the convention of my current, which I have labeled in pink, or I could also write it here as well. Any current which flows opposite to this convention would give me a negative potential difference. So I3 is flowing opposite to this convention. The potential difference across the resistor through which I3 travels is I write negative with it. And similarly, this circuit, I2 is also against my convention. So what I do with I2, it's also again a negative sign. And then I need to determine the sign of my EMF, E2. So I was telling that EMFs, there's this battery. If the battery is according to my sign convention, a battery like this, yes, you can choose any Azure convention. The answer would be the same, and I'll come back to this and I'll tell that how the answer would be the same. Just give me a minute. So a battery like this would give me would essentially would a battery like this tends to flow current in this direction. If there was a normal circuit attached, the current this battery would flow would be in this direction. This is how the battery would flow current. So if the current that the battery tends to flow is according to my sign convention. Now, according to my sign convention here, if I zoom this part and I like assess this, my sign convention says that the current between point C and X must be towards the right. But this battery tends to flow a current which is towards left from X to C. So it's in the opposite direction. So I write a negative sign along with E2. So I hope this is clear to everyone. And Mariam, is this clear to you now? Okay, so this is what I get. And then what I do is, obviously, since all of these are negative, so I just remove the negative signs. So I remove the negative sign. I don't know what's happening to the screen again and again. So I just remove the negative signs and I make them positive because I just multiplied all sides by negative. So this is what I get. And coming to Ali's question that we can choose the sign convention ourselves. Yes, we can. If I had chosen this sign convention, I would have gotten all my answers to be positive. It's like they would have already been positive for me. Oh, sorry. This is my current sign convention. Sorry. If my sign convention was reversed, if it was, if my sign convention was clockwise, then you could have applied this whole same thing and you would have still obtained this very same result. I3 was according to this flow, so it's positive. I2 is also according to this flow, so it's again positive. E2 is also according to this convention, so it's again positive. So that's what I'll get. So by the way, I prefer the sign convention that counterclockwise is positive. So that's what I follow. It's up to you guys, whatever you prefer. Just take one convention and just follow, keep following that. Okay, so the next part is between E1, E2, or I1 and I2 in loop ABC XYZ. So they're now talking about this big loop, which is this one. So we're now talking about this loop in blue. Just a second. Okay, so this time they're talking about this whole circuit, the one on the outer sides, AB, X, Y, Z, A. Okay, so this, now I take my sign convention, which is counterclockwise. So according to the sign convention, the direction of currents should be like this. Now I need to sum my EMFs and my potential differences. So first I write the EMFs. जी बैटरी से हमेशा करंट पॉजिटिव टू नेगेटिव ट्रेवल करता है, लेकिन अगर कभी उल्टा फ्लो कर रहा हो तो फिर हम ईएमएफ को नेगेटिव लेते हैं। उसका मतलब ये होता है कि हमने कोई ज़्यादा बड़े मैग्नीट्यूड का ईएमएफ लगाया हुआ है जो करंट को दूसरे डायरेक्शन में फ्लो करा रहा है। इसकी मिसाल बैटरी चार्जिंग की होती है। जब हम बैटरी गाड़ी की चार्ज करते हैं तो हम एक ज़्यादा ईएमएफ देते हैं जो उस बैटरी को चार्ज करता है। जी V2 में माइनस था, लेकिन क्या हुआ, वो माइनस सब तरफ था, तो मैंने पूरी साइड्स को माइनस से मल्टीप्लाई किया और वो कैंसिल हो गए। जी यानी बैटरी से हमेशा करंट पॉजिटिव टू नेगेटिव ट्रेवल करता है, लेकिन कभी कभार आपके पास बैटरी हो सकती है। इस पे ना अभी आ जाते हैं, अगर आगे कोई इस तरह का सवाल नहीं आया ना तो मैं इस पे बात कर लूंगा। तो फिलहाल जरा सवाल करो। ओके, सो मूविंग ऑन, between E1, E2 or I1 and I2, we need to like find the relationship between all of these. So first I just simply equate the EMFs. The EMFs involved in these are I1 E1 E2 equals I1 R1 I1 R and I2 R, and then again I1 R. This is I1, this is I1, so I1 R. Yes, you can leave the negative in part 2, लेकिन उसका कोई फायदा नहीं है, नेगेटिव वैसे ही कैंसिल हो जाता है, मसला नहीं है। मार्किंग स्कीम शायद में थोड़ा सा कुछ अलग लिखा हो, लेकिन बाहर चल जाएगा आंसर, कोई मसला नहीं होगा उसमें। Okay, so this is how I first write all of these parts, all the components involved. Now I need to determine the signs. So if I first look at the EMF E1, so the EMF naturally tends to flow current in from Z to A, and obviously that is my sign convention. So obviously E1 is positive. And then if I talk about E2, so this E2 tends to flow current in this direction. It tends to flow current from X to C, and my sign convention is towards the right. So it's opposite to my sign convention. So I write a negative here. So E2 is negative, equals I1 R1. I1 current is according to my sign convention, so I1 R is positive. Then I2 R. I2 R is opposite to my sign convention because I2 is flowing opposite to my sign convention. My current is supposed to flow to the right, and I from C to X according to my convention, but it's actually flowing from X to C. So I write a negative sign in front of I2. And then I1 CR, so I1 is positive. I1 is positive, so I1 CR would be positive. Okay, so Sunny, coming to your question, if you see, yeah, this is how it is. So okay, so E1 minus E2 equals I1 I2 I1 R1. Okay, so just a minute and then we'll proceed. Current from Y to Z is I1. Because that's very obvious. Uh, like if you just apply the sign convention, this is I2, this is I3, and this is obviously supposed to be I1. Like I just know this from this relationship. Just apply this relationship. What this tells me is that I3 equals I2 plus I1. So I just know it from this relationship. That's how I know this. I hope it's clear. Okay, so just a minute and then we'll proceed with the next part. Okay, so this is how we do this. And then coming to the next part, use Kirchhoff's law to state the relation, to state an equation relating these all these things. I1, I2, and I3. Just a second. Okay, so I do know that I3, some point where all these currents are merging. So if I take point W as my node is, let's say, so the current coming into here is I1. So Kirchhoff's law is sum of currents entering the sum equals the sum of current leaving the sum. So leaving the node. So the sum of currents entering node W is I1 plus I2, and the sum of currents leaving node W is I3. So that's what I write, I3. So that would be my answer. Okay, and the next part is use Kirchhoff's law to state an equation relating E1, E3, R1, R3, R4, I1, and I3 in loop WXY, ZW in this whole loop. The loop is WXYZW. So they're asking me about this outer loop. I'll remove, I erase this part. Outer loop. Okay, so this is the outer loop. Now, I do know the EMFs. One is E3 in this outer loop, and the other one is I1, which would be equal to I3R4 and I1 R1. Yeah, these would be the EMFs and the PDFs. The recordings would be uploaded on my YouTube channel, and I'll share the link after I've uploaded it in the group. Okay, so E3, E1, I3R4, and I1R1. These are the the registers and all those things that I need to involve. So talking about E3, is E3 or the current that E3 would generate, is it according to my sign convention or is it not? My sign convention states that the current should flow from X to Y, but E3 tends to flow current which goes from W to X. So obviously it's against my sign convention. So I would write a minus sign. And then if I talk about E1, so E1 tends to flow current which is from Y to Z. But my sign convention states that the current must flow from Z to Y. So I write a negative sign with it as well. So negative, negative. And then I talk about I3 R4. So, and yeah, I3 R4, and then there's another one, I3 R3. There are three resistors, not plus. Okay. So I3 is in the opposite direction of my sign convention. So I just write a negative on both these sides. And I1 is again against my sign convention. So I write it like this. So all of these are negative. So I would just multiply both sides by negative, and I'll get E3 plus E1 equals I3 R4 plus I3 R3 plus I1 R1. So that's what it is. Can I re-explain? Which part did you not get? The sign convention part or which part? Sign convention. Did you get how the PDFs? Why am I taking both directions negative? Which both directions have I taken negative?
Yeah, that's a doubt. I don't understand why are you taking both of the PDFs, the EMFs negative.
Both of the EMFs is negatives. Okay, so the reason for that is E3. If a battery is like this, what would be the direction in which current would flow out of this EMF?
From positive.
Yeah, towards upwards, right? In this direction.
Yeah.
And my sign convention states that I'm taking currents which are flowing downwards as positive.
Okay, so that's why we took it negative.
So it's against my sign convention, so I take it as negative. Yes.
Oh, so the sign convention must be for current, not for the EMF.
Hmm?
The sign convention must be for EMF or current.
Both.
Like for instance, I'm taking a clockwise, anti-clockwise as a negative. So it must differ or no?
If you're taking clockwise, anti-clockwise is. Can you repeat what you just said?
I'm taking the anti-clockwise loop as a positive and anti-clockwise and clockwise as negative. So that's why I got confused. Like I'm taking E3 as a negative and E1 as positive.
E3 and E1 both are like same. Like both are in the same direction. So both should have the same sign. Both should be negative or both should be positive. Depends on your sign convention.
All right, but sir, if you see the E3, it's pointing upwards, and E1 it is pointing downwards. That's why I was confused.
Yeah, E3 is pointing upwards because E3 is on the left. So if you like shift E3 towards the side, that would be pointing downwards as well. So they're both the same. If I stretch
All
this
right,
wire, if I stretch this wire and I ask you to draw all these E3 and E1 on this, so they would be in the same direction, right? So Rafe, is it clear to
yeah,
you?
yeah, I got it. I got it. Thank you so much,
Okay.
sir.
And Rafe, what about you? Is this clear to you too? Okay. So this is how we do this. And the next part is loop YZ WY. Y, Z, W, and Y. So this time my loop is supposed to be this. And again, I take my sign convention like this. This is my sign convention. Okay, and what are the EMFs that are involved? So one of them is E2 and the other one is E1. So that's an EMF which is involved there. Okay, and then uh, this equals what? E1, E2 equals the potential differences. So one of the potential difference would be I2, R2, and the other one would be, I'm not writing the sign yet. The other one would be I1, R1. Okay, so current I1 is opposite to my direction. So I make it a negative. Current I2 is according to my sign convention. So I leave that to be positive. So I2 is positive, I1 is negative. And then E2 and I1, E1. So E2 is again according to my sign convention, so I leave that as being positive, and E1 is against my sign convention. So I put a negative sign with E1, and that's what I just leave it with. So is it clear how I got to this answer? Okay, so I guess it's clear to everyone now. Now, two cells of EMF, E1 and E2 are and negligible internal resistance are connected into the network in A as shown in figure 7.2. Now again, Kirchhoff's law. Use Kirchhoff's law to state the relation between currents I1, I2, and I3. So, Asha, have we done this earlier? Yes, I think this is this question. Yeah, so we've done this. Apologies, it was pasted twice. So, like these were the two questions which are like about Kirchhoff's law, and there are many questions like this. So, if you've understood these two, then maybe you could solve other questions as well. So, this was important, and this is why we were doing Kirchhoff's law. Now, coming to the other type of questions, and these would be general questions where you would either be expected to use the formula of resistance, which is resistivity L over A, or the simple formula for voltage V equals IR, or I equals N Q A B. These are the formulas more or less that you would be using in the question that the remaining question that we'll be using will be doing today.
Sir, I have a question.
Yes, go
Will
ahead.
we be doing the potential divider circuit questions?
Yes, I have those questions and we'll be doing them tomorrow. And in
Inshallah.
fact, I think I did put some questions here today, but we'll mainly be doing those questions tomorrow.
Thank you, sir. Okay, sir. Inshallah.
Okay, so now the question is define the volt. And do I know the formula for voltage? Can you even tell me what's the formula for voltage? What's formula for V?
V is equals to IR.
And then there's another formula. That's the relationship between V and current, work done by charge. That's the defining formula for voltage. That's what defines volt. V equals IR is it just shows the relationship between potential difference and the current or the resistance. That's just a relationship equation. This is an equation which defines it. Okay, so V equals W over Q. Now the question could be of two types. They could either ask me about the quantity or the units of the quantity. So that's there's a difference between both of them. There's one thing which is voltage, and then there's another thing which is volts. What's the difference between voltage and volts?
Volts is a unit and voltage is the main phenomena.
Voltage is the quantity, and volts is how we measure that quantity. So voltage could be a potential difference or an EMF, and volts is how we measure it. We could say 5 volts, 6 volts, 10 volts. Volts is how we measure it. Like voltage is the actual quantity, and volts is volts. Better way, I don't know what do I call it. A voltage could be the name of the quantity, and volts are the units, or voltage is the quantity and volts are the units. uh, Voltage would be the unit, a quantity, and volts might be the units. Okay, so the question is define the volt. So in there could be two type of questions they could be asking you. Either they could be asking you about, no, that's why I'm telling. That's what I'm emphasizing in this. On this, the answer would have been different if they asked me to define voltage. Voltage is the actual quantity, right? So if they're asking me to define voltage, I would define it differently than if I were to define the units in which I was measuring that quantity. So voltage is work done per unit charge. That's voltage. So if they're asking me about voltage, which is the quantity, so I define it in terms of two other quantities, work done per unit charge. But if they're asking me about volts, so volts is not voltage, volts is the unit of voltage. So I need to define it in terms of the unit of work done, which is joules, and in the units of charge, which is coulomb. So voltage would be 1 volt is the quantity, or 1 volt is when 1 joule of energy is transferred to a coulomb of charge. So that's a volt. Or 1 joules of energy is transferred per unit charge. That's what a volt is. So when we're talking about units, we define it in terms of units. So we can't say work done per unit charge is volts. Volts is joules per unit coulomb, and voltage is work done per unit charge. So I hope this difference is clear to everyone. So there's the difference between quantity and the unit. Okay, so moving on. So a battery of electromotive force EMF 7 volts and negligible internal resistance is connected in series with 3 components as shown in figure 6.1. Resistor X has a resistance of 5.2 ohms. The resistance of the filament wire of Lymph wire is 6 ohms. The potential difference across resistors Z is 1.4 volts. Calculate the current in the circuit. So I need to find the current in the circuit, but I don't know the total resistance of the circuit, nor do I know the total potential difference of the circuit. What do I do? Anyone? Any idea? Like whatever we're doing in AS, most of these questions, the part where this formula would be involved, that would be something new. Other than this, everything is all what you've done before previously. So so the question comes, what's the difference between O level and AS? O level and AS, the difference is how you approach these questions. The formula or the method would be the same, but in AS they would expect you to like use your brains a little bit more and analyze the question a bit better than you were doing it in O levels. So this question is very simple. There is nothing, no new formula involved. You can just do it based on your knowledge of O levels as well. But there's some trick involved. Like they've just made the question a bit more difficult. So anyone with any idea how I can do this? Anyone? Okay, so I guess no one has any idea. So I'll just explain this. Okay, so I know the formula V equals IR, and V would be the potential difference across a region. I would be the current across this region, and R would be the resistance of that region. So I need to define the region on my own. I can't use the whole circuit because I don't know the resistance of the whole circuit. What I do is I take this as my region. So this is my region. This is my region. And what's the resistance of this whole region, which is in blue? What's the resistance of this? Can anyone tell me?
11.2.
Yes. 11.2 ohms would be the resistance of this region. Yes. And do I know what would be the potential difference across this region? Do I know this? Yes. No, not 1.2, 1.4. I know that the potential difference across, no, Mariam, not 7, 7 minus 1.4, because 1.4 is the potential difference across this resistor Z. So the potential difference across this part in blue would be 7 minus 1.4, which would be 5.6 volts. So 5.6 volts would be this, because the total EMF equals the total potential difference. So 7 volts, this blue region loses 5.6 volts and the Z region loses 1.4 volts. So this becomes 7 volts. So yes, Abdullah, Ali and everyone, you're right. It's 5.6 volts. Now I know the potential difference across this region, and I also know the current. So I could just use, and I also know the resistance. So I could use this V over R equals I. So V is 5.6 divided by 11.2. So can someone verify? I think the answer would be 0.5 ampere. Yeah, 0.5 ampere would be the current that would be flowing through this. And we also know that the current throughout the series circuit is the same. So 0.5 is this current, which is also this current 0.5 ohms, which is again this current, which is 0.5 ohms. So this is all there is. So you see, there was nothing new in this question. They were just expecting us to like use some method or think about it and find out a way how we could use this, how we could solve this. Or in other words, we could say that they were applying Kirchhoff's law. So the Kirchhoff's second law was that the EMF must be equal to the potential difference. So I could have said that current was supposed to be equal to, let's say, I. So my formula would have been like the formulas which you are applying above. So the formula would have been 7, which is the EMF equals Ix plus Iy. And I know the potential difference across Z, which is equal to 1.4 plus 1.4. So this is what I did. 5.6 equals I X plus Y. So this is what I did. The resistance of X and Y was equal to 11.2, 7.2, 5.6. So I got the same results. So basically this was, they were expecting us to apply Kirchhoff's law. Determine the resistance of resistor Z. Now I know that the potential difference across resistor Z is 1.4, and the potential difference would be equal to I Z, I times the resistance of Z. So I know the current 1.4 equals current, which is 0.5 times resistance of Z. So I could use this to find the resistance of Z, and it would come out to be something about 2.8 ohms would be the resistance of Z resistor. So I hope this part is again clear to everyone. Okay, so calculate the percentage efficiency with which the battery supplies power to the lamp. So we're just talking about the lamp. What's the total power supplied by the battery? How would I know that? The total power supplied by the battery. What's the formula for power? V2 divided by R. I don't know what you're referring to, but the formula I know is power equals V times I. So that's the formula for power. Now I need to find the input efficiency is output divided by input. Output divided by input. So output power is the power across the lamp. So output power would be the voltage across the lamp times the power, the current across the lamp. I I could also substitute this equation and write it as I square R. That's also another form to write it. This is like O levels. So I square R. Output power would be I square R. The current across the lamp is 0.5 ohms, which is squared, and then the resistance of the lamp, which is 6 ohms, divided by the input of the battery. The input of the battery is 7 volts multiplied by the current, which is 0.5. This would be power. So I was using different formulas. I used the formula of I square R above and use the formula of Vi beneath this. So both are equal to powers and are giving me the output and input power accordingly. So I just use this and I find the answer, and this comes out to be something as I think 3 over 7. I think, just verify it someone. And then the next part, the filament of lamp is made of metal of resistivity 3.7 times 10 to the power negative 7 ohms at its operating temperature in the circuit. Determine for the filament wire the value of A, where A equals cross-sectional area divided by length. So I know the formula. It's equal to resistance equal resistivity times L over A. They're asking me to determine the value of A, where A equals A over L. So if I rearrange this whole thing, A over L equals A. If I rearrange this formula and I make A over L the subject, I'll get A over L equals rho over R. This is what I'll get by rearranging this formula. And since these are similar to each other, I could say that my A is equal to rho over R. This is the relationship I could write. So not write, in fact, this is the relationship which I know. So A equals resistivity divided by resistance. The filament wire of the lamp is made up of metal of resistivity this. The filament wire of the lamp, we do know the resistance of the filament wire of the lamp, which is equal to 6. So I know the resistance, which is 6. I also know the resistivity, which is 3.7 times 10 to the power negative 7. So from this, I get the answer. Whatever it is, you can calculate. So that's how we solve this part again. So I hope it's clear to everyone. This was just a rearranging of the equation that was required to us in this part. Okay, so this question we'll be doing right now. Explain part 4 again. Okay, so in part A, they were just asking me to determine the value of a constant A, which is equal to the cross sectional divided by the length. Power part again for screenshot. Here you go. You can have the whole question. Okay, so Ali to explain part 4 again. So part 4 was they were asking me to give an expression A which could define which was equal to cross sectional over length. So I needed to find a value for that. What I did is I know this formula, which was resistance equals resistivity times L divided by A. I rearranged this into a form where I made A over L the subject, and that came out to be equal to resistivity divided by R. So from that, I equated that A must be equal to resistivity over R because that's what it's equal to. Then I knew the resistivity which they gave me, which was 3.7 times 10 to the power of negative 7. And then I knew the resistance as well of this lamp, which I knew from before, which was 6 ohms. So I just did that and I got the answer. So this is how I did this. I hope it's clear this time. Okay, so this is another question, and I'm skipping like this question because we'll do this in tomorrow's class. It's more related to internals and practical circuits. So okay, so state Kirchhoff's second law. We all know sum of EMFs in a loop equals sum of potential difference across the same loop. Resistance X has a resistance 4 ohms and resistance Y has a resistance 1.5 ohms. So I know the resistance of both these resistors. The resistance R of the variable resistor is changed until the voltmeter in the circuit reads 0. Calculate the current I in the circuit. Now, the thing is, the resistance R of the variable resistor is changed until the voltmeter in the circuit reads 0. What would this mean? Anyone having any idea? Yes, potential difference is 0, obviously. But what actually happened to the circuit? What actually happened is that this there was this loop, and then there was this loop as well. So it was arranged in such a way that the potential difference across V just happened to be 0. Sliding contact will be closer to the fixed end. There is no sliding contact involved. Sorry, get to what you're trying to say. Okay, so the resistance of the resistor R is changed until the EMF is like this. So what this basically tells me is if I make this loop, in this loop, the EMF across V is supposed to be the potential difference across this voltmeter is 0. That's what I know. So which means like if I make an equation for this, EMFs equal potential difference. So EMF would be EMF would be 6 volts. EMF equals PDs. So EMF is 6 volts, and then there's this a 4 ohm resistor which has a current flowing in this direction, which I know obviously because that's the direction of I. So 6 equals 4 times I plus the potential difference across the voltmeter. So voltmeter, which was equal to 0, so I just write nothing. But this is what I'm supposed to get. Just a second. So did everyone follow this? What was happening in this question? This was my loop. Or let me draw it in a better way. This was my loop. This was my loop, and I know that the potential difference across this voltage, this voltmeter, it's 0. The potential difference across this voltmeter would be equal to 0, meaning that this 4 ohm resistor and this 6 ohm 6 volt battery must like all the EMF was going into this battery. So I get this equation: 6 equals 4 times I. So 6 over 4 equals I, and I get 1.5 to be 1.5 amperes to be equal to I. Did everyone get how I found I, the current in the circuit? I could have done it another way as well. I could have used this outer circuit as well, but I had too many unknowns. I also didn't know the resistance of this resistor R, so that's why I didn't use it there. So I hope this is clear to everyone. Like, this is important stuff. If you're not getting this, do ask. Okay, so then the resistance of resistor R. So now we get into the next part of the circuit, and I make my convention, which is this. I'm not erasing the other part because so that just so that it's clear to everyone. Okay, so this is what I have now. They just, if I need to equate the EMFs to the PDFs, PDs to the potential difference, so I'll get EMF1, which is there's this one EMF in this loop, which is just the 6 volts battery. 6 equals the potential difference. First would be I R, the second would be 1.5 R. So this is what I'll have. It's 1.5 I. So I know, I just found out it was equal to 1.5. So 1.5 R plus 1.5 times 1.5. So I do all this equation and I get 3.75 divided by 1.5 equals R. So from this, I'll be able to find R. I replaced PT with IR. Yes, potential difference is equal to IR, na? V equals IR, where V is the potential difference. So this is the formula, and that's all I did. I just applied this formula. So if this is clear. Now I've done this. The next part is determine the ratio of the average drift speed of electrons, of free electrons in X, and the average drift speed of electrons in Y. I just need to do this. I have the formula with me. I equals NQAV. I make V the subject. And I get V equals I over NQA. This is what I get with me. Now, the next thing I do is I just use this and I make some substitutions. So the voltage across X divided by V, not voltage, sorry, the drift speed velocity across X divided by drift speed velocity across Y. I do this equation, I get current across X divided by number density of X, charge of X divided by and area of X. And then I divide this further by the current across Y divided by N Q area across Y times X. Area across Y. Sorry. This is what I get. Now I need to like cancel things out. They've told me in the question that diameter of wire X is twice the diameter of wire Y. I know this relationship that diameter of X equals twice that of diameter of wire Y. And if I find the areas out, so area equals diameter pi d square over 4. That's how areas are related to each. That's the formula of area. So yes, so area of X would be pi dx square divided by 4, and the area of Y would be pi dx square divided by 4. Sorry, not dx square, dy square. Pi dy square. Yes, you're right. It would be 4 times, but I'm just getting to the derivation of y and how it would be 4 times it, 4 times the area. So now I substitute, make this substitution. I make this substitution and I get area of X equals pi times 2 dy square, 2 dy whole square divided by 4. So I get pi multiplied by 4 dy square divided by 4. 4 and 4 cancels out. So I get pi dy square. This is what I get. Area of X equals this, and area of Y equals pi dy square over 4. If I now compare both these areas, I get this relationship that AX equals 4 multiplied by AY. Sorry, I made another mistake. I don't know why I'm writing things wrong. This was AY from here. So if I compare this, I get this relationship that AX equals 4AY. Now if I look above, all these were connected in series. So IX and IY were the same. So they cancel out with each other. Similarly, N is the same, Q is the same, it's from the same material and everything's the same. So what I end up is with an equation of AY divided by AX. This is what I'm left with. Now I know the relationship that AX equals 4AY. By the way, I just made a mistake. The diameter of wire X is twice the diameter of wire Y. So diameter of, no, I did it right. Okay, so I now know the relationship AX equals 4AY. So I just substitute that. AX equals 4AY. AX was equal to AY divided by AX. AX was 4AY. So this becomes 1 over 4. So the ratio is 1 over 4. Okay, so I hope this part is clear to everyone. Yes, 1 over 4. The resistance of the variable resistor is now increased. State and explain the effect of the increase on R on the power transformed by each of the batteries. So if the resistance of the variable R is now increased, I need to explain the effect of the increase in R on the power transformed by each of the batteries. Increasing the resistor R, what would it do to the overall resistance of the circuit? It would decrease the resistance. And if the total resistance of the circuit would decrease, what would happen is that the current in the circuit would decrease. And now if the current has decreased, the power across each batteries, the formula for power across each batteries is power equals VI, where V is a constant. Voltage remains the same because voltage is associated with the battery, not with what the current is. So the EMF is the same. If by increasing the current I've decreased I, so I've also decreased the power. So the power transformed by each of the batteries would also decrease if I increase the resistance of by the variable resistance R. So that's how I do this. So that's all there is. So I hope this part was clear to everyone. And like this is where we'll end the class of ours of today. So if anyone has any questions regarding what you've done, feel free to ask. So I guess no questions. So in that case, we'll then end. And inshallah, we'll have a class tomorrow where we'll be doing questions regarding internal resistance and practical subjects. Recording, yeah, I'll upload this recording as soon as possible. So probably by tonight, maybe check YouTube around 2 a.m. or around that time, or maybe around 12 or 1. I don't know. In an hour or so, I'll upload it hopefully. Okay, so welcome everyone. Jazakallah. Assalamu alaikum.